This is Unit 2, Lesson 7, Part 2. This lesson is on rates of change, and this video will be on straight line motion connecting position, velocity, and acceleration. So we're starting out with a first look at particle motion. So we talked about particle motion in the last video, and we need to establish some vocabulary and terminology that connects our three parts that we're looking at: the position, the velocity, and acceleration of an object in motion. These foundations will be used throughout our course. So normally we use S of t to represent the position function relative to some origin or wherever it started from. And it's a function of time, and that is called the position function. So when you're talking about the position function, you want to think about an object that's moving along a straight line. Later on, if you're going to go in a more pure science or engineering level, you'll talk about the motion of a particle that's moving along a curve. But we're not going to get into that at this level. So we're talking about moving along a straight line. These objects can move either horizontally or vertically. So what are some examples of objects, either natural or man-made? And I'm sure some of the things that come to mind is any kind of vehicle. So like a car can move horizontally. People do when they walk. Even geographical features like rivers, we think of them as moving horizontally. Things that move vertical are such as a bouncing ball, a rocket, something dropped, so an object dropped off a building because it's affected by gravity. So those are some things we think about. So sometimes you also see x of t instead of s of t, because we're talking about an object that moves horizontally. So we use x of t, and then if it's moving vertically, we sometimes break that into y of t instead of s of t. So that gives our position relative to the origin of an object as a function of time. As the object moves, its position changes over time, which you are all very aware of. Therefore, the velocity function is the change of the position function over time. So these words should seem very familiar. Change of the position function over time. And of course, we're talking about the derivative. And we say that the velocity function, v of t, is the same as s prime of t or x prime of t. So let's go back through and look at some ideas about motion and direction as related to velocity and the direction it's moving. So, of course, here is our definition of the velocity function. It's ds dt, or s prime of t, and it is the limit as the change in t approaches zero of our difference quotient. So let's see which direction a particle will be moving depending on the sign of our velocity function. So if our velocity is greater than zero, and let's just do first the horizontal line. If the velocity is greater than zero, the object is moving to the right, so it moves right, because that's considered our positive direction. If velocity is less than zero, we say that it moves to the left. And if the velocity is zero, the particle is at rest. Now, what if we're talking about a vertical line motion? So if our velocity is positive, it moves up. If it's negative, it moves down. And again, if the velocity is zero, it is at rest. And that looks like at vest, like I'm dressing my particle for a party. So at rest, there we go. Okay, now, here's what can be a little confusing. Remember, speed is a little different. Speed doesn't indicate a direction, and is not always synonymous with velocity, even though we take it that way. So the speed of an object is either positive or zero. We mean it's either moving or it's stopped. So you want to be careful about that. So speed tells you how fast an object is going, but not the direction. So speed only measures the rate at which position changes. So it's always positive. So it is defined as the absolute value of velocity. So you can't tell from the speed the direction that the object is moving. All right, now acceleration is, and we're using these words again, the instantaneous rate of change of the velocity. It tells how quickly the body is speeding up or slowing down, or how fast velocity is changing. So, of course, that makes it the derivative of velocity, which in turn makes it the second derivative of our position function. And we usually use the letter a of t. And you want to remember this, just because an object's velocity is 0 doesn't mean the object is stopped. Think about the cruise control in your car. You're not accelerating or decelerating, but you're still moving. All that means is that the velocity isn't changing. The acceleration function behavior can be summarized in a table like we did with the velocity. So talking horizontally, if your acceleration is positive, that means you're kind of, think of this as being able to put your hand on it. It's being pushed, I don't know why I didn't put an H in there, pushed to the right. So it's been given a little push. If the acceleration is less than 0, it's like it's being slowed down, so it's being pushed to the left. And if the acceleration is 0, it means you have constant velocity. Not 0 velocity, just a constant velocity. And we can make the same kind of argument if we're talking about vertical line motion. So if your acceleration is greater than 0, it's being pushed up. If it is less than 0, then the vertical line motion is being pushed down. So it's like you're trying to slow it down. I probably should put upward. And then finally, if it is 0, again, you have constant velocity. Okay, so one thing to remember, and this is pretty important, and because we're going to have a lot of questions going forward about looking at the velocity graph or the acceleration graph. Is the object speeding up, slowing down? What direction is it headed? And eventually, what is the final position? And we're going to do one of those problems in a little bit. So I just want to go through this. So the speed of an object is increasing when it's moving away from the x-axis of a velocity time graph. Now you want to make sure that you notice that this says a velocity time graph. Likewise, the speed is decreasing when the object moves towards the x-axis. Without the aid of a graph, we know the following relationships. Now these, again, you have to pay attention to. They can be a little much, but once you work with them a little bit, it's no big deal at all. So the big thing to remember are these two statements right here. If velocity and acceleration have the same sign, you're speeding up. If velocity and acceleration, if they have opposite signs, the object is slowing down. So even though your velocity may be negative and your acceleration is negative, you're actually speeding up in the negative direction because they both have the same sign. So it's like you're heading back towards where you started and you're speeding up that process of moving back towards where you started. But if you're moving in a positive direction and your acceleration is negative, it's like someone's putting the brakes on your car, so you're slowing down. So you want to remember that if your velocity and your acceleration are both positive, the object speed is increasing. If your velocity and your acceleration are both negative, the speed is still increasing. It's just increasing in the opposite direction. Now, if the velocity and acceleration have opposite signs, so let's say you have a positive velocity, a negative acceleration, you are decreasing. And the same thing is true as if your velocity is negative, but your acceleration is positive, you're still decreasing. Okay, so let's take a look at this problem, which is very long. I think what I'll do is I'll do the first half of it in this video and finish the second half in the other video. We'll see how it goes. Okay, so this is example 5. The graph at right shows the velocity of a particle moving along a coordinate line. Assume that the positive direction is to the right. Answer the following questions. And any few of these could definitely be a question on the AP test. So being able to read a graph and interpret what you're seeing is a big part of calculus. So number 1 says when the particle is moving at a when is the particle moving at a constant speed? So what you want to find is the part of time where it is flat. So if you notice right here, from 0 to 1 second, the velocity graph, because that's what this is, it's not a position graph, it's a velocity graph, the speed is constant. So we can write it this way, 0 is less than t, which is less than 1, or you can write it as an interval. Whichever way is fine. I'm going to write the rest of them as intervals. I'm just more comfortable that way, but if you want to use inequality notation, you can. Okay, so when is the particle moving to the right? So that needs to happen anytime the velocity is positive. So there is only a very small section of the graph where the velocity is positive. So that's from here to where it hits the x-axis right there. So the answer to that question is going to be from 0 to 2 seconds. You have positive velocity, so the particle is moving to the right. So when is it moving to the left? Everywhere the velocity is negative. So you can see from here all the way along that path, we have negative velocity. So that is going to be from 2 to 5, where it's moving to the left. Let me clean this off a little because I'm going to be writing on it a lot. Okay, next question. When is the particle speeding up? That's going to be when you have two things happening. If you look at this graph, you want to have your velocity and your acceleration either both be positive or both be negative. Now, in this case, you can see from 1 to 2, we have a negative slope here. We have a negative slope here as well. And then from 3 to 5, we have a positive slope. So along this line, acceleration is greater than 0. Along the blue lines, acceleration is less than 0. So we need to find a situation where the velocity and the acceleration have the same sign. Well, we know it's not going to be between 1 and 2 because there the velocity is positive. And between 3 and 5, the acceleration is positive, but the velocity is negative. So the section of the graph where the particle is speeding up is going to be between 2 and 3, because at that point, our velocity is less than 0, and also our acceleration is less than 0. So when those two match, we know that we are speeding up. So that's the only section of the graph we have that. So when is it slowing down? And we'll see that when we have opposites. So as I had mentioned, here we have a positive velocity, but a negative acceleration. So that's one section. So from 1 to 2, it's slowing down. And also along this part of the path, because we have a positive slope, so we have positive acceleration, but the velocity itself is negative because we're below the x-axis. So it is also slowing down between 3 and 5. And if you want to get a sense of it, here at these 2 points, the velocity is 0. So it's slowed down to that 0, and again, along this other path, it's slowing down to a velocity of 0. So next, when is the velocity increasing? And we can see that where our acceleration is greater than 0. And that happens right along this path. So that's between 3 and 5 units of time. We don't know what it is. I might have said seconds, but I don't know if it is seconds. Okay, so moving on, when is the velocity decreasing? So that's going to happen when the acceleration is going to be less than 0. So that happens, that is happening between 1 and 2, and also between 2 and 3. Okay, so are the answers to questions 6 and 7 the same as my answers to 4 and 5? And explain. Now you'll notice that they're not the same. 4 and 5 do not have the same answers, and neither do 6 and 7. So the reason for that is because, so right now, and the reason is velocity increases when acceleration is positive. Okay, next couple questions. How fast is the particle moving at time t equals 4, and in what direction? So let's take, and then what is the particle's velocity at time t equals 4? So let's do those together. So let me erase what I have on here. So we're talking at time equals 4. So that's right here. So we want to know, again, how fast is the particle moving and in what direction? And secondly, what is the particle's velocity? So that's the easy one. So let's do that one first. So we can see here, this is a velocity graph. The value is, this point is 4, -5. So I'm going to write that my velocity is -5. Now, how fast is the particle moving at time t equals 4, and in what direction? Since this is a negative number, it's going to be moving to the left, and how fast will be the absolute value of that, which is 5. So those are going to be my answers to numbers 9 and 10. So how fast is the particle moving? It's moving 5 units per whatever, and it's moving to the left. And what is its velocity? So v of 4 is going to equal -5. So the next two questions, let's do 11 first because it's a little different. What is the average velocity over the time interval 2 to 3? So what we want to do is find the average velocity. So we're going to average our speeds at 2 and at 3. So we can see here at 2 we have a speed of 0, and at 3 we have a speed of -5. I'm sorry, -10. So we are going to average those together. So we're going to get 0 minus 10 over 2, and we're going to get -5. And then when does the particle change direction? You can see it does that in 2 spots. Even though the second one we don't know what's going to happen later, that would happen when the velocity is 0. So here and here, but we have no data after this. So this isn't really a change of direction at this point, but that's what we would look for at 5 seconds. So our only change of direction is right here when v of t equals 0, because it was moving in the positive direction, it's at 0, and then it's moving at the negative direction. So our answer to number 12 is going to be that at t equals 2, and because v of 2 equals 0. So number 13, how far does the particle move during the first and during the first second, and which way? So looking at the picture again, we can see that during the first second would be this section of the graph, and it's moving to the right. and how far. So it is traveling 5. Let's just make a unit. Let's say 5 feet per second times 1 second, or 1 unit. So those wouldn't matter. So it's covering 5 feet. It's kind of hard to talk about that in generality sometimes. So during the first second, it's moving 5 units. And which way? It's positive, so it's moving to the right. How far to the right does the particle go, and when does it arrive there? So what we see is that we have these 2 different distances here. So we have our 5. Let me erase my graph again here to clean up some of this. So we have our 5 units right here. So there's our 5 units. And then what we have to figure out is if we want to find the distance traveled, we have to find the area here. Okay? Because this area, if you want to think of it that way, is going to be the area of this rectangle, which is 5 by 1, so we get 5. Then we're going to find the area of this triangle, so it's going to be 1/2. 1 unit is the base, and the height is 5. So we get 5 halves for that. So we're going to add those together. So we get 5 plus 5 halves, which is going to equal 7.5 units. And when does it arrive there? At t equals 2 seconds, because that's when it stops moving to the right. And again, looking at the graph, and I apologize for having to scroll so much, here at t equals 2, this is where the velocity is 0, and it becomes negative after that moment, so it's changing direction. Okay, 2 more questions. So the next 2 say, what is the total distance traveled by the particle, and then what's the particle's position after 5 seconds? So the total distance traveled by the particle is going to be the positive direction, which we already have. So let's write that down now. So we know it's already traveled 7.5 units, and then we have to look at the negative distances traveled. So we look at the triangle here from 2 to 5 seconds. So we know it has a height of 10, and it has a width of 3 as a base. So the area is going to be 1/2 10 times 3, so we get 15 units. So that's going to be the other, that's going to be the other part of what we add to what we have, the 7.5 for the right, and then to the left, it is going 15 units for a total of 22.5 units. And then what is the particle's position after 5 seconds? So what we want to see is, from what we did in the previous problem, that it moves 7.5 units to the right, and then over the next 3 seconds, it's going left 15 units. So it's actually negative 7.5 units to the left of the start. Okay, so now what I'm going to do is I am going to have you guys pause and let you answer 17 through 28, and then I will post the answers. Okay, here are the answers for 17 through 28. We will be going over these in class, but I wanted you to have a chance to try to figure them out on your own. And I will finish our discussion of Lesson 7 in our next video.